Hello, everybody. Mr. Hinnon here, and I am going to do a little bit on free body diagrams. Okay, so I have my little Joker head here, and he's going to help me out as I do it. And if you notice, I also have a picture of a Joker here that we're going to be using. So I'm going to use this little video down here to kind of cover some stuff at the same time. So the first part is let's assume that my Joker is just sitting here on the table, and it's just plain at rest. So sitting on the table at rest. What would this free body diagram look like? Well, a free body diagram is actually one in which you are representing all the forces acting on it. So if I were to come along and draw those, I would probably come along and say, okay, I'm going to draw a vector pointing straight down that would represent the force of gravity. So let's grab a pen so I can actually write this a little bit faster. So I would call this the force of gravity. We also call this the weight of an object. So that would be one that would be acting on it. The other one is obviously he's sitting on the table. He's not just falling. So if you just had a picture like that, it would be this situation. Boop. Falling Joker. So he would be accelerating towards the ground at 9.8 meters per second squared. We don't want that. So there has to be another force acting on him. And in this particular case, it's the table. The table is holding him up. We actually would have an upward force acting on him. And we could just call this the force of the table, but it actually has another name. We're actually going to refer to it later as a thing called the normal force. And all that means is that it is a force that is perpendicular to the table that happens to act straight up. So it's perpendicular. So this would be parallel to the table. This would be perpendicular to the table. Now, to be extra picky, these two forces should be equal in size to indicate that this object is at rest. If one was larger than the other, then he would be accelerating in this direction. For example, if I grab him here and I accelerate him upward, I would actually say that this top force, which is now probably not really a force of the table anymore, this would be the force of my little pinch on him. This force would have to be larger. So I'll just call this my pinch force. Let's change that. There we go. Pinch. And it would have to be larger. So since I can't really make that one larger, what I'm going to do is I'm going to make gravity be a slightly smaller force. So we'll just say the force of gravity is a smaller value. So the force of gravity is smaller than my pinch force, and therefore he would accelerate upward. So when I had this and I went whoop, accelerated him upward, then my upward force is larger than my downward force on the Joker here. If instead I started him up here and I'm still pinching him, I'm still holding him, but I had him actually accelerate down to the ground, I don't actually have to push him down to the ground. I am just pinching and applying less force as he accelerates towards the ground. So in that particular case, then my pinch force here, let's get rid of that one, would be smaller. So I might have just a little pinch force like that. Now, if you notice, I drew a little red dot on him, kind of where his nose would be. And the reason why I put that on there is that's why I'm kind of considering his center of mass. We often do all the forces around what we call his center of mass, just to make it a little bit easier for us. What if I was moving him at constant speed, though, like constant speed up or constant speed down? Well, if he moves at constant speed, those forces are equal. So remember that Newton's first law says objects in motion or objects at rest are going to happen unless you have unbalanced forces. So if you have balanced forces, if you have equal forces, then that's what's going to happen. Okay, now let's get rid of those just real quick here. Bye-bye, bye-bye. And I'm going to put them back in. So I'm going to start off with him sitting on the table here. Okay, let's actually put him right over there. Okay, and let's put these in again. So let's put in my force of gravity. Let's make the force of gravity about this big. And we'll put in the force of the table. We're going to make them be equal. Okay, so those are equal forces. I'm not drawing real straights, but that's okay. Okay, so now I've got that happening. But now I'm going to come along and I'm going to push on him, and I'm going to push him at a constant speed across the table. So I'm going to start him over here and just constant speed. Ready? Constant speed. Okay? Got it? Constant speed. So what's happening there? Well, obviously I am pushing on him. So let's add another force. I'll call this a pink force. And technically it would be a push kind of in this direction, but I always draw it away from here. So let's say there's some kind of push. Call this FP, push force. Now, if those were the only three forces acting on him, he would be accelerating because you would have a net force. This pink FP would be applying a force and causing an acceleration. That's Newton's second law. But I don't want that. I want him moving at a constant speed across the floor. So how do I do that? How do I get that constant speed? There has to be another force acting on it. Let's make this one purple. And in this particular case, it is opposing this pink push force. How do I get a opposing force? We call this friction. That's going to be happening down here on the surface. It's always parallel to the surface. So it would be acting in this direction. And this would be the force of friction. And that would be for a object, the Joker, moving across the table at constant speed. This is probably the most complicated type of free body diagram you'll see on the worksheet that we have going on. Now, what if I instead accelerated him? What if I went like that across there? All that means is that my pink force over here must be greater than my force of friction. So I'm accelerating him across the table. What if I didn't? I toss him off the table. What if I push on him, but I let him slow down? So he starts out, he's moving, and then he comes to a stop. Or if I push him and let him come to a stop on its own, then this pink force would just be smaller. So I hope that helps a little bit on free body diagrams. Have a wonderful day.